All right, so example 6 is referring back to example 5. We did example 5 yesterday. Remember on example 5, it said that 10 bacteria are growing by doubling every single hour. Doubling every single hour. So we came up with this model that said the number of bacteria at time t, and you all chose B. The initial value is 10, that's our A value. And because it was doubling, the growth factor, or the base, was 2, right? Times 2, times 2, times 2. And it was every hour, so it was just to the tth power. So that when t is 0, we get 1 factor of 2. When t is 0, we just get 10. When t is 1, we get 1 factor of 2. When t is 2, we get the second factor of 2, so on and so forth. So example 6 now says, what if we take the same initial bacteria culture from above, that is the 10, but we change the rule by which they duplicate? In this case, what if they tripled every 2 hours instead of doubling every single hour? Would that be at a faster rate or a slower rate? Should be a little bit slower, right? Because doubling every hour would be the same thing as quadrupling every 2 hours, and here they're tripling every 2 hours. So it's a little bit slower, but the question is, what would the model be? Well, let's see. If we start with our template, I'll use the same letter from above. B of t is your starting amount, A sub 0, times the base to the tth power. Does the initial amount change? No, so it's still 10. If we're tripling every 2 hours, what would be an appropriate growth factor? 3. Good. Now, we want it to triple every 2 hours. So how do we reflect in the equation that it's tripling every 2 hours instead of every hour? Multiply by t, divide by 2, multiply by 2, multiply by 2, half 2, 1, 17. Thanksgiving.
Yay.
Yay. Actually, here's what we're going to do. If you're not sure, you're going to create some ordered pairs based upon the rule that's given how they grow. So here we go. The first ordered pair was at t equals 0. We had 10, right? So there's an ordered pair, 0, 10. If it triples every 2 hours, then at t equals 2, 2 hours later, we should have how many? 30. You triple 10, and you get 30. In another 2 hours, at t equals 4, it should be what? If it triples every 2 hours, triple 30 is 90. So you could go on and generate as many ordered pairs as your heart's desired. How many does it take, though, for us to find our 2 values of A sub 0 and B? It only takes 2, right? So I'll just take the first 2. Because remember, if you have this ordered pair, that's a very special one, right? That's the y-intercept. That one tells you immediately what the initial value is, so it's 10. So what we could do then is just kind of get rid of that. If I plug the 10 in only, I still have times b to the tth power. So there's my model with my initial value of 10 plugged in. Now I can plug in any other point, either the 230 or the 490. It doesn't really matter. I'll choose the 230 just because the numbers are a little smaller. So when I plug in, I get 30 for b of t equals 10 times b to the 2th power, to the power of 2. And now all we have to do is algebraically solve for b. So if we do that, we'll divide through by 10, and we get 30 tenths, also known as 3. Now I'll extract the square root from both sides. When I extract square roots, or even roots in general, I need to at least consider plus or minus, right? We need to at least consider it. Does the negative value make sense for us in this problem? No, because we're finding the base of an exponential, and remember the base has to be either bigger than 1 or between 0 and 1. So now we'll just take the square root of 3. Is 3 a perfect square? No. So remember what we do if it's not a perfect square, instead of taking the square root of 3, we'll just raise both sides to the 1/2 power, and we end up with 3 to the 1/2. Remember that? If it's not a perfect root, just leave it as the nice base raised to the fraction power. And then all we have to do is plug that in right here to get our model. So b of t is going to equal 10 times b, which is 3 to the 1/2, raised to the tth power. Now, we don't want to stop here because the way it's written, we still have our base as the square root of 3. So what we do is then absorb that fractional exponent into the exponent of the equation. And we combine the 1/2 and the t here by doing what? Add, subtract, multiply, or divide. Multiply. So you could skip this step, right? You work enough of these, you could skip that step. You can go straight to the final model. 10 times 3 to the 1/2 tth power, or I'll just say t divided by 2th power. So there you go. When in doubt, create some ordered pairs, plug it in, and find it. Now let's see if we can infer something here. This 10 was the initial amount, right? It tripled every 2 hours, so the base, of course, is the tripling effect. But because it tripled every 2 hours, and I think one of y'all said this, all you have to do is take your exponent and divide it by the number of hours it takes to triple, which in this case was 2. By doing that, notice when t is 0, you get 10, your starting value. But when t is 2, 2 divided by 2 is 1. You get 1 factor of 3. When t is 4, 4 divided by 2 is 2. You get your second factor of t. So by putting divided by 2, we're saying now every even number, or every multiple of 2, we're getting another single factor of 3, which triples it, which is exactly what we want, okay? So in the future then, if you know how it grows, you don't actually have to create ordered pairs. You can go straight to this model. Initial value times growth or decay factor to the t divided by the time it takes to whatever the base is, in this case triple. All right, so in this case, what are the units of t, just to make sure? Hours. T is measured in hours. The units of the independent variable are going to be very, very important, all right? So what we're going to do now before we move on to the next one is what if the population tripled not every 2 hours, but every 7 hours? Well, let's see. B of t would be the same. We're still starting with the initial 10. It's still tripling, so the base or the growth factor is still 3. But if it's going to triple every 7 hours, ODI, what would be the new exponent? Thank you. T divided by 7, right? T divided by 7. Perfect. Oh, by the way, it said how long is it going to take to reach 500,000? I'm going to go ahead and skip that because I think you could do it, right? You would just set this equation, 10 times 3 to the t halves in y1. You'd sketch 5,000 in y2, change your y max, and then find where they intersect, okay? It ends up being like 19 hours instead of where it was up here, 15 hours. But you would do it the same way we did it on example 5. All right, part B. This is part A. Part B. What if we change the rule now and it tripled every day? It tripled every day. Well, let's see. B of t then, it would still be 10. That's still the initial value. It's still tripling, so it's 3. But now if it's tripling every day, it would be t divided by what? 24. Because we're still measuring time in hours, we got to do a little stoichiometry, a little unit conversion. 24 hours is 1 day. Okay, good. And I'll just put here t is still in hours. Part C. What if it tripled every 20 minutes and we're measuring time in hours? Well, let's see. It's still 10. It's still 3. But now it's t divided by... Oh, yeah, very good. We need to figure out 20 minutes is how many hours? It's 1/3 of an hour. Very good. 20 minutes is 1/3 of an hour. So you would do t divided by 1/3. But, of course, that looks gross because it's a complex fraction in the exponent. So whenever you're dividing by a fraction, it's the same thing as multiplying by its reciprocal. So instead of t divided by 1/3, we'll do t times 3, which is to the 3/10 power. Yeah. Which makes perfect sense because remember the 3 in front of the t is going to compress your graph of 3 to the t by a factor of 3, making it very narrow, which makes it grow a lot faster. So if it's tripling 3 times an hour or every 20 minutes, it's going to be faster. All right, so that's how you can do it. T is measured in hours. T is measured in hours. Now, at some point, if you're the one collecting the data and you're making your model, selecting the units for the independent variable is very, very important. Let's say that you were measuring it in hours, but you noticed that it didn't triple except every 2 days or every 3 days. You might not want to use hours anymore, right? You might want to change your independent units to days or something like that so that you don't have fractions, okay? All right, let's do example 7 then. This is kind of rapid fire. We got a few of them here. Yeah. No, I'll tell you what the units need to be on the free response. And I'll make it so that you maybe have some fractions, yeah. So example 7 will be more like what you'll see on the free response. I will tell you what the units are. Determine the exponential function of the form y equals a times b to the t that satisfies the following conditions. Define the units you'll use for t. All right? So we'll do 7a together, and then you'll do 7b. We have an initial value of 7, and it's increasing by 32% per day. So instead of just calling the function y, that's kind of boring, y equals, let's call it t. No, that's a bad one because we're using t of t. How about h of t for holiday of t, since we're about to go on holiday? Yay. So if the initial value is 7, that's our a value, right? That's the y-intercept. So we get 7 times. If it's increasing by 32% per day, is it going to be growth or decay? Growth. Now, 32%, remember, is not the growth factor. It's the growth rate. So in order to convert it to a growth factor, remember, we take the 1, which is 100%, and we either add it to the decimal version if it's growth, or we subtract the decimal version from it if it's decay. Yeah, so this is going to be 1 plus 0.32. Or you know what? I'm just going to get rid of that and call it 1.32. It's 100% plus 32%, so it's 132%, which is 1.32. And it's per day. Per day. So if we let t be in days, defining our unit, then it would just be t divided by 1, right? T divided by 1 is just t. So days would be probably the best unit to use here, right? So we wouldn't have to have fractions. But let's do a little mental exercise here, and let's deliberately change the units. What if I wanted t to be in hours? Well, let's see. That's going to be h of t. It's still going to be 7 times. It's still going to be 1.32. But now it's going to be t divided by, 24 hours equals 1 day. So I'll divide it by 24. All right, let's go the other direction now. What if I want t to be measured in weeks? Well, let's see. I'll have h of t. The initial value is still 7. The base is still 1.32. It's the growth factor. And now it'll be t divided by 1 day is how many weeks? 1/7. Good. If it's per day, that's per 1/7 of a week. So t divided by 1/7 is the same as what? T times 7, right? Or 7 times t. So you could go straight to that if you want. Dividing by a 7th is the same as multiplying by 7. So in one case, we have a nice integer. In the next case, we have a fraction. We're dividing. And in the next case, we're multiplying. So I'll typically do that. I'll give you a unit that's bigger or smaller than the comfortable one. All right? Very good. Next one, you do on your own. Initial value 427, decreasing at that rate per year. Write the model and tell me what units you're using. All right, let's see how you did it. I called mine Q of T, QT. Okay, just changed the name to kind of keep it exciting. The initial value is 427, so that's A. That's easy. It goes in the front. Now we're decreasing by 0.427%. So this is the decay rate. So it's going to be 1 minus that as a decimal. So are we subtracting 0.427? No, we are not. It's 0.427%, which is a tiny percent. We need to subtract it as a decimal. So that's minus 0.00427 to the tth power. And if you measure t in years, you won't have to modify your exponent. You can leave it as t. So that turns into 427 times, good morning, thank you. What'd you get, Dane? 0.99573. Okay, cool. To the tth power. To the tth power. So years would be probably the most appropriate one there. Let's go ahead and convert it from years. Let's go ahead and do centuries. Ooh, that's a unit you don't use that often, huh? In centuries. So it's going to be 427 times 0.99573 to the what power? Well, 1 year is how many centuries? 1/100th. Good. So dividing by 1/100th is the same as multiplying by 100. Yeah, there you go. So it would be to the 100th power if you're measuring in centuries. Let's do one more. Let's see if we're measuring t in days. If we're measuring t in days, it's going to be 427 times, see, Allie, 0.99573 t divided by 1 year is how many days? 365 and 1/4. Ish, right? Ish. Leap year, ish. If you just put 365, that'd be fine. Okay? It's actually 0.25 something, because we don't have leap years every 4th year. We have it in some years that are multiples of 4. Yeah, like 2000 was not a leap year, because if it's like divisible by 100 or something like that, we skip the leap year, because it's not a perfect terminating decimal, 365.25. It's 0.25 something, something, something. So there are corrections to the correction of every 4th year. Okay, so you got the idea. Let's do part C now. The initial value is 18. It quadruples every 13 minutes. Let's call this W of t for wow of t. The initial value is 18. Now, instead of giving you the growth or decay rate, I'm telling you it quadruples. That would be the growth or decay what? Factor. Good. And it's growth, right? Because it's getting bigger. So the base is going to be what? 4. And if quadruples every 13 minutes, then if I let t be in minutes, my exponent will be t divided by 13. Good. T divided by 13 every 13 minutes. Bless you. Let's do one more. Let's do t in seconds. It would be W of t equals 18 times 4 to the t divided by. 13 minutes is how many seconds? 13 minutes is how many seconds? Well, you would multiply by 60 seconds over 1 minute, which gives you what? 780. So it would be t divided by 780. You get the idea, right? The independent variable is very important for these types of problems to define what units you're using. All right, go ahead and do D on your own. You can do it. I promise you can do it. I'm going to call my function m of t for marathon of t. Why marathon? What's our initial value? 26.3, which, if we were playing that little game, would be n of m in an m, number of miles in a marathon. Okay, so 26.3. If it's halving, what would be a nice base? 0.5 or 1/2. Now, if you put it as 0.5, you don't need parentheses. If you ever have a fractional base, you want to put it in parentheses. Because without the parentheses, if you write the exponent, it looks like it's just the numerator to that exponent.
If you have 0.5, you could put it in parentheses. Is that wrong?
Oh, that's fine too. Yeah. It's better to have the parentheses and not need them than to need them and not have them. Yeah, so that would be fine too. If we measure t in fortnights, why not, right? Let's bring back the fortnight unit. What would the exponent be? T over 3, right? T divided by 3. But since most people don't know what a fortnight is, let's go ahead and let t be in weeks. So that would be 26.3 times 1/2 to the t divided by 6. Good. Because if 1 fortnight is 2 weeks, then 3 fortnights is 3 times 2, which is 6 weeks. All right. I think you get the idea there, right? So we don't need to keep going. Questions on that? Writing models quickly from verbal descriptions. You can either be given the growth or decay rate and or the growth or decay factor, and you will be told per whatever time. And of course, now you know how to justify or how to modify the exponent to make it happen. But if you ever find yourself forgetting, you can always go back to the old faithful, generate some ordered pairs based upon how it's growing, plug your 2 ordered pairs in to get a system of equations, and find the model that way, okay? And I think that's good enough for today. So we will stop right there and give you a chance to go to your worksheet and do the problems in the worksheet that deal with this type